Hello everyone, and welcome to another webinar from our Rocky in Action webinar series. My name is Guilherme Turezo, and I am part of the Rocky DEM support team. Today, we are going to make a short presentation about bucket elevators and show how we can use DEM simulations to improve this equipment and their operating conditions. I hope you enjoy. Well, in many industrial applications, the particle transportation can be a challenging task. And transporting the bulk material to a different level in massive quantity, it requires different devices and very specific machinery. These kind of machines are called bucket elevators. And this equipment are used for unloading procedures, conveying at two different heights, and for feeding and receiving material. And they are essential for bulk material transportation. And bucket elevators are designed to work with maximum capacity, to lower power consumption, and to prevent unnecessary equipment maintenance. And for this reason, DEM simulation can show how these devices work with different materials and under different operating conditions. Additionally, with Rocky, we can account to high fidelity particle shapes and wide particle size distributions, and these can increase the simulation accuracy considering different bulk media during an equipment design, and therefore to lead to a better product development. Now we can jump into the bucket elevators industrial applications and how they can be modeled inside Rocky. Bucket elevators, they can be found in many industries such as mining and metal industry for coal and ores transportation, inside the cellulose industry for shredded wood and wood chip transportation, into pharmaceutical for raw material and additives transportation, for food and agriculture industry, for seed and grains transportation, and as well as for other industries. And in industrial applications, it is expected to the bucket elevators to perform with high transportation capacity, with high translational speed, and not to damage throughout the transportation cycles. And this way, we can obtain the best performance for a bucket elevator without having excessive damage and misalignments. And with these objectives in mind, we can optimize these devices through the EM simulations in Rocky and also obtain crucial information about equipment power consumption, wear on the bucket surface, and total efficiency. Today, we are going to show how we can set up a DEM simulation of a bucket elevator and do some post-processing analysis in Rocky. And we'll begin by importing the elevator geometry, and then we'll create and edit a feed conveyor from Rocky's embedded conveyor templates. Later, we'll set up the particle inlets for periodic motions, and then we'll create a periodic motion frame. Next, we'll replicate a geometry for periodic motions, and after running the simulation, we'll show how to calculate an average material weight in each bucket by adding custom expressions inside time plots and visualize particle trajectories. So by starting a new project, we're going to name the study. So we'll set the study name as bucket elevators. We'll set all the physics models as default for this demonstration and start importing the geometries. So we select the geometries and it will be asked to us to save the file or even replace. So we set the import unit and drag the geometries into the workspace. This will create a 3D view and we'll be able to visualize the geometries. And for better visualization, I will set the transparency for these geometries and only color the bucket. Now we see the bucket is placed in its initial position. And instead of importing feed conveyor, we can go to an embedded conveyor template and dimension inside Rocky our feed conveyor. So we're going to set the transition length, the loading length, the belt thickness, and this is also followed by its orientation. We can rotate it and also place these feed conveyor accordingly to our geometry. So we set the horizontal, vertical offsets. We can set also the skirt board uh, dimensions as its length, the skirt board height, and this will prevent the particles to leave the feed conveyor once they reach the belt. And also we can edit the feed conveyor box, its wall thickness, and at the end we can edit the head pulley, its face width, and also its diameter. And now with all set, we can set the belt motion. And for this case, we'll set the belt motion as 0.75 meters per second. So the particles will reach this velocity when reach the belt. And now we're going to create some inlets. So we're going to have two inlets, one regular one, and one will inject the particles periodically. So the regular one we'll name as regular feed. We'll center it accordingly to our our feed conveyor. So the regular feed will send it in front of our feed conveyor. We'll rotate it, we'll set its length and width, and we can duplicate the regular feed and create the surge feed. We'll only need to recenter it and re-rotate the surge feed. So now we have two inlets for our particle injection. And now we go to the motion frame creation. So we create the motion frame. We name it as bucket motion. And this bucket motion frame will be a periodic motion. And this periodic motion will have a series of 4 motions that will be in sequence, 2 translation and 2 rotations. And this will perform the bucket elevator motion. So we'll begin by rotating the motion frame, and we can see better on the motion preview. On the motion preview, we can make the geometries transparent too for better visualization. And we see the motion frame on its original position. And we can start by enabling the periodic motion and set the periodic motion period exactly the period of the bucket elevator motion. So it will be 8.98148 seconds, and start with the first motion that will be the translation. The translation, we set the start time and the stop time. We set the fixed velocity, that will be 1.15 meters per second. And at the end of our belt, it will rotate. And so we set our start time, the exact time as our stop time of the translation. And also we set the stop time of the rotation. And we set to the angular velocity for its rotation. And we need to do the same procedure for the motion frame to go downwards. So we set a translation to the start times and stop times. We set the velocity 1.15 meters per second. And at the end, we do a rotation by setting the start time, and the stop time will be exactly our periodic motion period. So we see that these times match. So it will be our last motion for our periodic motion. So now playing it, we can see that our motion frame will perform the bucket elevator motion. And we can go into the bucket and the geometry tab and select the motion frame for the bucket. So we see now the bucket is performing the periodic motion, but we want to have 20 buckets. And we go inside the geometry, we set replication, and the number of replication will be 20. We set a periodic replication because it's a periodic motion, and set the replication period the same time of the periodic motion period. So now we have our bucket elevator motion, and we can go on the materials. The materials, we will set them as default, and we'll change only the materials interactions between the boundary and the particles. We'll set the static and dynamic friction as 0.5, and we'll create our particle. Our particle will create a spheral polyhedron particle. So we'll choose a spheral polyhedron. We'll set the shape, and the number of corners will be 10. And at last, we set its size. So the maximum size will be 0.15, and the minimum size will be 0.05 with 10% of its mass into the PSD. So our particle is already set. And now we can jump into the continuous injection creation. So we're going to have two injections, one regular and one periodic, as I said. So the regular injection will set the entry point as the regular feed, and set the particles, and its mass flow rate will be 70 tons per hour. And we can duplicate the regular injection and also create the surge injection. And the surge injection, of course, will have its entry point, this surge feed. The mass flow rate will be 40. And now we will set the periodic checkbox to be as a periodic injection. So it will start at 5 seconds of simulation, and its period will be 10 seconds, and injection duration will be 5. With this, is everything set for our simulation? We can go into the solver tab. And into the solver tab, we only set our simulation duration, and we can leave the output frequency as it is. So we run the simulation, and once it is done, we can begin post-processing it. So this is a simulation has run all the way. And we start creating a cube in our particles. So the cube, we need to rotate, we need to place it accordingly. And with this cube, we are going to gather 6 buckets at once. So gathering 6 buckets at once, we can calculate the total mass of particles, and then divide by 6 to have an average weight for particles. So going inside the cube, we go into properties, we choose the particle mass, and we set the time plot and the sum calculation. So now we're having the sum of all the particles inside this cube. And going to table, we can add an expression for the mass per bucket and divide the sum per 6. So this will have the dashed line will show the average weight per bucket, that it will be 15 kilograms. And going back into our 3D view, we can set the time bar as 5 seconds. So we'll begin our calculation at 5 seconds for our particles trajectories. So we go into particles processes and set the particles trajectory. Into our particles trajectory, we set the number of time steps and the particle stride. So for every 5 particles, we're drawing a particle trajectory, and we can color these particles trajectories by the particle mass. So we can see the trajectories colored by the particle's mass, and it is very important to do some analysis. Well, that's the end of our simulation demonstration. And the results from this simulation, they can lead to critical information and better bucket elevator design, and also prospect many operation issues. And for example, they can help you to determine the material mass flow injection of the system and the correct velocity for the buckets. It will determine the best size and shape for the buckets too. And also we can calculate the maximum capacity of the system and the particles trajectories. And these, therefore, it will help to determine the size of our receiving box. We can also prospect worn regions of the equipment and calculate the efforts by the elevators and much more. Well, that's the end of our Rocky demonstration. And now I would like to invite you all to attend our next 15 minutes webinars that will take place on the upcoming weeks. The next one will be on September 22nd about packaging. And see you there. And thank you everyone for attending our today's session. I invite you also to take part into our poll, into our survey, excuse me. And please connect with us in one of our channels. And if you have any questions, send us in the chat. Thank you.